Hi everyone, welcome to our second video presentation on the theory of computation. I am Kentaro Takahira, will present the first part, and my friend Lee Haobo will give the second part. In this presentation, we will explain two important concepts, Turing machine and unsolvable problem. Let's start with Turing machine. So what is Turing machine? Turing machine is an extended computational model compared to finite automata or push-down automata. This machine is used as a formal model of the modern computer. Compared to push-down automata, it only has states and input tapes. However, there is a major difference. First, in the Turing machine, the head can move in both directions, left and right. So the Turing machine can read back the content on the tape. Moreover, the Turing machine can write content on the tape. For example, it is possible to overwrite C on the position of B. This function gives the machine unlimited and unrestricted memory and extend its possible language space. So then, when does the machine holds? In the Turing machine, there's a state called halting state. Suppose the machine reaches the halting state, then the machine holds. Please note that it is not guaranteed that machine always holds. It may run forever. So let's see how Turing machine works with a concrete example. 5 elements can formally define a Turing machine: possible state, alphabets, transition function, and state and halting states. Here, suppose we have this input tape and transition function. Please note that the transition function of the Turing machine is different from the previous computational model. For example, this transition function means that when the machine reads A on the state Q0, then move state Q1 and write blank on the tape. Also, the transition function means that when the machine reads blank on the tape Q0, it then moves the head to the right. This is denoted as a right arrow. In the Turing machine, the head never moves automatically. Okay, so how does the Turing machine works? Suppose we have this input tape, start symbol 3A and blank. First, it reads the start symbol on state Q0, so it moves ahead to the right and let the state same. Next, it reads A on state Q0, so it writes the blank symbol and moves the state to Q1. This process will continue until it reaches the halting state. When the machine reaches the halting state H, finally, the machine will halt. So let's take a look at another example. In this example, the input tape is the same. However, the transition function and possible states are different. First, the machine reads the start symbol on the state Q0, moves the head to the right, and lets the state the same. Next, it reads A on the state Q0, moves the head to the left, and does not change the state. This was the same state when the machine started. Consequently, the machine makes the same move as it first moved. Here, you can see that this process continues forever and never reaches the halting state. This is an example that Turing machine never halts. Okay, so let's talk about language. What is the corresponding language to Turing machine? Turing machine can define two different kinds of language. First, let's look at the language space defined by Turing machine that always holds. Suppose that there is a Turing machine such that an input is a word in a language L, then it holds on the yes state. On the other hand, if an input is not a word in the language L, then it holds on the no state. Then we say that this Turing machine decides the language L, which is called recursive language. Please note that Turing machine always holds whether an input belongs to a language L. Next, let's look at another language space. Here, suppose that there is a Turing machine such that if an input is a word in the language L, it holds on the state. On the other hand, if an input is not a word in the language L, then it never holds. In this case, we say that this Turing machine semi-decided the language L, which is called recursively enumerable. Here, the important thing is that in this case, Turing machine does not give you a way to determine the membership of a word. Since the Turing machine never holds, even though you have been waiting for a pretty long time, the machine is always possible to eventually halt. Let's look at the relationship between different languages. It can be proved that recursive language is part of recursively enumerable language. You can always construct corresponding Turing machine from a recursive language that semi-decides this language. The new Turing machine will be like if the original Turing machine holds on yes, then the new Turing machine holds on any state. On the other hand, if the original Turing machine holds on the no state, then the new machine never holds. On top of that, it can be proved that context-free language is part of recursive language. The proof is also based on construction method. Suppose we have a context-free language L, then we can always convert it to a specific Chomsky normal form. Then, for any context-free grammar written in Chomsky's normal form, we can always construct a Turing machine. Therefore, it can be said that context-free language is part of recursive language. We will finally formulate the hierarchical relationship of language based on previous discussion. From the small language space, they are regular language, context-free language, recursive language, and recursively enumerable language. Also, the corresponding recognizer is essential too, since they give you a computational model for each language. On top of that, please note that even recursively enumerable language cannot represent all of the possible languages. So next, let's talk about the properties of Turing machine for computational model. Even though there are some languages that Turing machine cannot represent, we argue that the Turing machine is a proper model of computation. Why is that? This is because any other computational model cannot define more language than the standard Turing machine. For example, there are many attempts to make a variant of Turing machine as shown in this slide. However, all of them proved as powerful as standard Turing machine. Hence, it is near universally accepted that if some algorithm exists to carry out computation, then the same computation can be carried out by a Turing machine. This is called Church-Turing thesis. Lastly, let's talk about closure property. Recursive language is closed under the following 5 properties, such as union, concatenation, clean stir, intersection, and complementation. However, recursively enumerable language are not closed under complementation. The intuition is that Turing machine, which semi-decides L, does not hold for some word and runs forever. Therefore, you cannot make the complemented Turing machine, which can hold on the non-holding input for the original Turing machine.
Okay, next I will introduce the unsolvable problems and the summary of video presentation 2. Let's go back to the key question of this class again. What problems are not solvable by computers in principle? The answer in this class we will learn is the halting problem, some undecidable problem, and the tailing problem. Before introducing these problems, we first introduce the universal Turing machine. First, we can understand universal Turing machine in this way. Turing machine is the math model for the algorithm, and the universal Turing machine is the math model for computers. A universal Turing machine U simulates a given Turing machine M on the string omega. It takes both the encoding of the Turing machine and the corresponding input, and the U behaves like U holds on the input M omega if and only if M holds on omega. For better understanding, U can be seen as a computer, and M is the program and omega is the data. So how to encode a Turing machine? For states, we use a Q and binary ID to encode them. If the initial state is always 0. For symbols, we use A and binary ID to encode them. And then for transitions, we encode them as quadruple. Moving on, we next talk about the decision problems. A decision problem is a yes or no question in many instances. You may think a yes or no question is too simple, right? However, every computational problem is either equivalent to a decision problem or it is at least as hard as a decision problem. As for decision problems, we have decidable and undecidable problems, ignoring p-time for now. So how can I know if the problem is decidable or not? A problem is decidable if there is a Turing machine that always holds on the corresponding language. Not all problems are decidable, and undecidable problems exist. We can think about the Turing machine is a finite representation, so there are countably Turing machines. And we have uncountably languages. Hence, some are not recursive. Thus, the unsolvable problem exists. Recall the hierarchy of language. We can also know the border between solvable problems and unsolvable problems. If you are interested, you can also refer to the link for the list of the unsolvable problems. Then we will learn about some unsolvable problems and learn how to prove them. To prove a problem is undecidable, we use the reduction technique. First, we find a problem A that can be reduced to B. Second, assume B is decidable. Third, use B to solve A, which is known to be undecidable. Finally, we can prove B is undecidable. Okay, then we use a halting problem to illustrate how to use the reduction technique. The halting problem is one of the first problems that proved to be undecidable. First, reducing to the h1 that m holds on the input string m. Secondly, we assume that h is a recursive, and by the definition, there exists a Turing machine mh that decides h. Thirdly, using the Turing machine mh as a subroutine, we construct a new Turing machine that decides h1. Finally, contradiction, and we prove that h is not recursive. Besides the halting problem, we have learned some other undecidable problems. Let LM be the language semi-decided by M, and then we have the following problems. To prove these problems are undecidable, use the reduction technique too. Okay, the last problem I like to introduce is the tiling problem. If we are given a finite set of tiles, infinite copies of each tile, and we have fixed corner and adjacency rules, is it possible to tile the first quadrant? It is also an undecidable problem. Okay, that is the video presentation too, and then let me give the summary. First, we introduced the Turing machine, and the Church-Turing thesis shows that Turing machine is a general commutation model. Then we introduced the recursive language is decided by the Turing machine, and the recursively enumerable language is semi-decided by the Turing machine. Finally, we introduced the undecidable problems, including the universal Turing machine reduction technique, and then we proved the halting problem, tiling problem, and some other undecidable problems. That's all. Thank you.